Welcome, science enthusiasts, to Weep on Science. I'm Ethan Walker. Ever wondered how hypersonic ballistic missiles or combat drones in the Middle East find targets with terrifying accuracy? Do they use satellite navigation systems like Google Maps or the US controlled GPS? The surprising truth is absolutely not. The era of US military dominance in the skies has officially ended. Today, we uncover the scientific evidence. When America cut off GPS access in war zones, advanced weapons from nations in conflict with the West still hit targets precisely. How is this possible, physically and technologically? The answer isn't on land. It orbits serenely at an altitude of 21,000 kilometers above us. This isn't the US military's global positioning system. This is something far newer and more secret. The world knows it as China's Dragon Eyes, the third generation Beidou satellite navigation system, or Beidou-3. In this Science and Geopolitics documentary, we'll expose the deepest secrets behind military satellite navigation. We'll delve into the physics of space navigation, from orbital mechanics to ultra-precise atomic clocks, and how Albert Einstein's relativity prevents a missile from missing its target. Prepare for a deep why not science's analysis that will challenge your understanding. We'll grasp how independent space technology permanently alters global power balance in the Middle East. Let's begin by understanding GPS and why this system can be a fatal weakness for a nation's military. For decades, the world lived under the illusion that GPS was a free, neutral global public utility, like the air we breathe. Technically and legally, the global positioning system is a pure military asset, owned, operated, and fully controlled by the US Air Force, now under the United States Space Force. Because GPS is a military system, its operators possess absolute capabilities, selective availability, and regional denial. This means, with a few button presses at a military base in Colorado, the US military can drastically reduce GPS signal accuracy or even shut down service entirely in specific conflict zones. Imagine a scenario where a nation's military launches advanced drones or ballistic missiles toward enemy targets. Suddenly, GPS navigation signals are cut. Without satellite guidance, the missile's internal inertial system begins to drift. Within minutes, the advanced weapon veers far off target, falling somewhere uselessly. This is the strategic nightmare many nations unaligned with Western policies realized. Dependence on GPS is akin to surrendering their necks to the enemy. This realization sparked a new arms race, not on land or sea, but a race to build independent space-based navigation constellations immune to intervention. Entering Phase 2, we dissect the anatomy of China's solution to this monopoly problem, the Beidou-3 satellite navigation system. Unlike US GPS or European Galileo, which rely on one orbit type, Chinese space engineers designed Beidou-3 with a unique, far more complex hybrid constellation architecture. To grasp this design's genius, we must learn a bit about satellite physics. GPS places all its satellites in medium Earth orbit at approximately 20,000 kilometers. Satellites in MEO continuously circle Earth, completing 2 orbits daily. Beidou-3, however, uses a combination of 3 different orbits simultaneously to create maximum coverage. Beidou-3 comprises satellites in medium Earth orbit for global reach. Satellites in inclined geosynchronous orbit form a distinctive figure-8 path, providing enhanced coverage over the Asia-Pacific region. And satellites in geostationary Earth orbit appear fixed at a point directly above the equator relative to Earth's rotation. This combination offers immense tactical advantages. By placing satellites in geostationary orbit, Beidou ensures China, Asia, and the Middle East are permanently monitored 24/7 by the same satellites. In large-scale conflicts, these geo-satellites never dip below the horizon, providing a very strong, uninterrupted navigation signal for allies on the ground. This hybrid architecture makes the Beidou system highly fault-tolerant. If one MEO satellite is damaged or destroyed by anti-satellite weapons, IGSO and GEO satellites instantly cover the blind spot. This is the highest level of military redundancy applied in space. Science enthusiasts. How do satellites actually tell us our position on Earth? The physics behind it is called trilateration. Navigation satellites don't know where you are. They continuously transmit radio signals containing their identity and the precise time the signal was sent. When a receiver in a missile or your smartphone gets the signal, it calculates how long the radio signal took to travel from satellite to Earth. Since radio signals travel at the speed of light, approximately 300,000 kilometers per second, travel time multiplied by light speed gives accurate distance. Knowing the distance from one satellite, the receiver knows it's somewhere on the surface of an imaginary sphere with that radius. With a signal from a second satellite, its position narrows to an intersecting circle of two spheres. With a third, it becomes two intersection points. And with a fourth satellite, the absolute three-dimensional position is finally found. But here lies the biggest problem. Since light travels so fast, even the smallest time calculation error is fatal. A time error of just 1 microsecond, 1 millionth of a second, causes a missile to miss its target by 300 meters. A 1 millisecond error, and it misses by 300 kilometers. Unacceptable. Ordinary watches or even advanced quartz clocks can't be used on navigation satellites. They need humanity's most accurate timekeeping device, the atomic clock. Inside every Beidou-3 satellite, there isn't just one, but several advanced atomic clocks working in parallel, cross-correcting each other. The presence of these atomic clocks differentiates regular communication satellites from military-grade navigation satellites. Without them, the entire system would collapse. Entering Phase 4, let's dive into the quantum physics marvels within the atomic clocks. Beidou-3 satellites are equipped with two main types: rubidium atomic clocks and active hydrogen maser atomic clocks. They work by counting microwave transition frequencies of electrons shifting energy levels within atoms. This is the universal, unchangeable standard of time. Beidou-3's hydrogen maser clocks are even more accurate, losing only 1 second every 3 million years. A terrifying level of precision. This horrific precision allows China's military and Beidou-using nations to pinpoint 3D coordinates with accuracy down to the centimeter. But science enthusiasts, merely having accurate clocks isn't enough. The universe has its own strange rules. Placing these super-precise atomic clocks in space, orbiting Earth at thousands of kmh, forces us to confront Albert Einstein's greatest physical laws, the theory of relativity. Two relativistic effects occur simultaneously. First, special relativity. The faster an object moves relative to an observer, the slower time runs for that object. This is kinetic time dilation. Because Beidou satellites move so fast in orbit, their atomic clocks tick approximately 7 microseconds slower each day compared to Earth-bound clocks. But wait, there's more. The second effect comes from Einstein's general relativity. Gravity isn't a pulling force, but a curvature of space and time. Stronger gravity means slower time, weaker gravity means faster time. Beidou-3 satellites orbit at 21,000 kilometers, where Earth's gravitational pull is much weaker. Consequently, their atomic clocks tick approximately 45 microseconds faster each day than military command centers on the ground. Combining these, special relativity slows clocks by 7 microseconds, while general relativity speeds them up by 45 microseconds. The net result: satellite atomic clocks run constantly 38 microseconds faster per day compared to clocks on Earth. 38 microseconds, a tiny number, yet this is the pinnacle of physics' beauty and terror in modern military technology. If Chinese scientists and engineers ignored Einstein's relativity and didn't recalibrate atomic clocks before launch, what would happen? This 38 microsecond daily error multiplied by light speed results in an 11.4 kilometers accuracy shift in just 1 day of operation. That's 300,000 kilometers per second times 0.000038 seconds. An 11 kilometers error means a missile targeting a military base could hit a civilian area or empty desert. By day 2, the error becomes 22 kilometers, rendering the system militarily useless. Pure science truly controls the course of warfare in this modern era. Now, Phase 5. Beidou-3 reveals its true fangs, fundamentally differentiating it from US GPS, integrated two-way short-message satellite communication, a secret feature built into its hardware. This isn't smartphone SMS. This is a tightly encrypted military tactical data transmission system, letting field units not only know their position, but report it back. Let's analyze its tactical implications in a Middle East war scenario. Imagine Iranian kamikaze drones operating in isolated mountainous terrain, no internet, no cell towers, conventional radio blocked. How do they coordinate? Using Beidou-3 chips, each drone not only receives navigation guidance, but sends short messages. New target coordinates, fuel status, low-res radar images back to the satellite. The satellite then relays this data to ground command or directly to other drones. This transforms every military unit, ship, or missile into an encrypted communication node in a giant space network. This two-way communication feature has a transmission capacity of up to 1,000 Chinese characters or approximately 14,000 bits of data per second. This is more than enough to send real-time updated GPS coordinates to a flying missile. The two-way SMS feature makes Beidou's hybrid orbit architecture sensible. GEO satellites, stationary above the equator, act as giant space communication towers. They serve as an unbreakable data relay backbone for all of Asia and the Middle East. The US recognizes this threat. Opponents' ability to communicate independently without Western infrastructure renders military isolation tactics obsolete. Cut their internet, they use their navigation satellites as military emergency internet. This is operational resilience at its most brilliant. Furthermore, because these communication signals are transmitted on the same frequency band as the main navigation signals, enemies will struggle to block communication without simultaneously destroying navigation. This innovation puts Beidou-3 a step ahead in the evolution of network-centric warfare, not just knowing where we are, but integrating our position into the entire fleet's situational awareness. This system is designed for total war, where all civilian infrastructure is destroyed, leaving space as the only communication route. Even the US military is accelerating its own satellite architecture development to catch up. But for now, Chinese satellites have a firm grip over the Middle Eastern skies. Iran's medium-range ballistic missiles benefit from this uninterrupted, high-precision data stream for terminal phase maneuvers. They can dynamically alter course, relying on space-based coordinate updates, to evade ground-based air defense systems. Entering Phase 6, we discuss the true unseen battlefield, electronic warfare. Why are Beidou-guided Iranian missiles so hard to jam or mislead by advanced Western electronic defense systems? Jamming is basic. The enemy transmits high-power radio waves at the same frequency to drown out weak satellite signals, like trying to hear a whisper in a loud rock concert. Chinese military engineers equip Beidou's military navigation signals with frequency hopping spread spectrum, or FHSS. Instead of a fixed frequency, Beidou signals hop across thousands of different frequencies every second. This complex pseudo-random hopping pattern is known only to the sending satellite and military receivers with valid cryptographic decryption keys. Jam one frequency and the signal is already on another. Beyond jamming, a more dangerous threat is spoofing, where enemies transmit fake navigation signals that look and feel identical to the real ones, to trick missiles into veering off course. Beidou-3 military signals are protected by high-level asymmetric military encryption. Each navigation data packet is digitally signed by the satellite. When a missile receiver gets the signal, it verifies this digital signature using a secret public key.